So yeah, so we'll continue from where we sort of left off last time, and I have also asked Melissa to assist me whenever there is a more technical math doubt. So let me just recall what we did, but please stop me at any time if there is any question. So just to review that, we started with some what we call a gentle blossomed quiver. So I'm just giving you an example here where there are 6 external vertices, which are as usual denoted as hollow vertices, and 3 of these black solid vertices. And then by looking at, they are labeled by all the walks which have precisely one peak at that vertex and nowhere else. And so this vertex gets labeled with 1, 3, 1, 4, 1, 5. So I'm going fast because this is what we did last time, but please ask if something is not clear. And then we have a data set that for all proper walks, which are basically walks which do not begin and end in adjacent points like 1, 3, 1, 4, etc., we could make this chart of where are a peak and a dip. So 1, 3 has only a peak at this vertex, which I denote as 1, 3 dot, just to distinguish from the 1, 3 walk. So and similarly we could catalog. So for every path that you could write, you would have like some peaks and the dips. And then we saw that all the paths which were compatible, like there was many sets of paths. In particular here, if you work it out, we worked out 5, n equal to 5 example, but it's exactly the similar. And you can see that there are always like sets of 3 walks which are compatible with each other in the way we explained last time. And the set of all such compatible walks give us same as the set of all triangulations, in this case of a 6-gon. And that is a combinatorial geometry, which is called the Associahedron. So is there this was a recap of lecture 1. Is there any question about this, or is it okay? Okay, and also we introduced something called the Arkani-Hamed. So let me just give one specific example in this case, that you could look at any subquiver. For example, let's focus on this one. So if you just focus on the 1, 4 dot and ask, okay, what are the walks which have precisely either a peak or a dip at that vertex and nowhere else? And you can quickly check that there are only 2. So there is a walk 1, 4. So there is one walk 1, 4, which has a peak at 1, 4 dot and no dip, and there is exactly one walk 3, 6, which has a dip at 1, 4 and no peak. Now, so you see that now, so these 2 chords, you can ask, so there are only 2 chords, and these 2 chords, if you draw them in the same hexagon, then it gives us something which combinatorially looks like a one-dimensional polytope. And this is one example of a one-dimensional Arkani-Hamed. It's one dimension because just the fact that there are 2 vertices, and you can go from one to the other by one flip, so it's one dimensional. And this Arkani-Hamed is labeled by what we started with, which is 1, 4 dot. Sorry. So these are the class of combinatorial geometries we kind of understood, just starting from this specific class of quivers, and it gives us a unique Associahedron, but it could give us many different Arkani-Hamed depending on, you could start with any subquiver like this one, either of individual vertices or like this one, etc. Is this point clear? So yeah. Yeah. So Associahedron is something where every vertex, it's a combinatorial geometry, where every vertex is labeled by a complete triangulation of an n-gon. Arkani-Hamed is a very general class of polytopes where every vertex is labeled by some specific type of dissections of the n-gon. But you don't, what this quiver is teaching us is that you don't have to look, you cannot look at all dissections. So here is an example that I dissected my 6-gon into 2 quadrilaterals. You would have thought that it means I have 3 possibilities of dissection, 1, 4, 3, 6, 2, 5. But from this quiver, we see that it only picks out 2 such dissections, and it generates one Arkani-Hamed. So, what is the definition? So Arkani-Hamed definition is exactly this, that it has every vertex which is labeled by a partial dissection of an n-gon, and the adjacent vertices are obtained by some flip rules, which I am generating from this quiver. You are asking an independent definition. So here in this case, the independent definition is start with the dissection. Now look at all the edges which are adjacent to it. So it's this one, this one, this one, and this one. And now you say, okay, what are all the chords I can draw which are not which touch these hollow vertices, which are not adjacent to each other? There are only two possibilities that generated this. So you do it for any partial dissection. So for example, take, just to give another example, take this as my beginning dissection. So now this would correspond to taking a subquiver, which is I think this one. And so you could read off this rule from this subquiver, but you could also directly read off the definition of the Arkani-Hamed from this prescription that label all the edges which are adjacent to this dissection. So the only thing you exclude is this guy. And then now you draw all possible split of my sixgon into triangle and quadrilateral, which come only from these vertices. Exactly. Also has more data. Yeah, so that's why in the case of Associahedron, I just wrote it as it's just quantified by the number of vertex of the polygon or number of dissections you need. Here you need the reference data also. Yeah. Yeah. No, they are not. No, it can be subquiver. So it could be like two of them or more of them. They are always in a precise sense of projection, but they need not be faces of Associahedron. Yeah, if you take full, you get Associahedron. You take any like subquiver based on one or two dots, like they not be adjacent. You could take these two also, for example. Then you get anything you will generate using this rule will be one Arkani-Hamed. But everything just comes from this. And so that's why you know there is obviously a relation between Associahedron and Arkani-Hamed, but it's not a phase. It is, as we will understand, it's like a specific projection. Yeah, that was the starting point of defining this quiver.
Can we have multiple lines between the...
No, not for this one. This is my beginning object. So it's a linear, what we call linear quiver, in the sense that between these there is only like a single line. In general, of course, you could have, and that would give us more complicated geometries that we will look at, for example, for one loop, etc. You need more general quivers. This one are not, yeah. Yeah, it can be phase, but it need not be a phase. It's not always a phase.
So the flip of this would be
Flip of which one?
The other one, right?
Yeah, so this one has the Arkani-Hamed is two-dimensional. The dimension of polytope is always number of chords you have. So there are several. I think the corresponding Arkani-Hamed is a pentagon in this case. But or a square. It could be either a pentagon or a square. I mean, one has to draw it. Just look at all the flips and you can draw it. Yeah.
What type of quantities can you compute?
So say that again.
What quantity can you compute?
Yeah. So we will come to that's a point of the lecture. We will see that all of these. Right now it's all combinatorics, right? But we will see that they are really, the point is that these are really sitting as some natural objects in kinematic space. So we want to find them, and then they're in some sense either a volume or the canonical forms, as Melissa explained, give us amplitudes for some theory, some or the other. We right now don't know what theory. So we will see that all the Arkani-Hamed that we discover in kinematic space, they always give us amplitude for some tree-level amplitude for some theory. But right now we have not made any connection to any physics. We have not said anything about the spectrum of the theory or anything. So, yeah, I hope I reached there. Okay, so. Exactly. Yeah, exactly. Yeah, that's true. But they are all projections. So yeah, okay. Anyway, they can all be obtained as some slices of Associahedron, always. So the master polytope is going to be Associahedron, and we will get Yeah, I think in the end, I hope one of the message of the lecture will be there is one mathematical object which is generating a large class of amplitudes. And there are many operations we can do which give us these amplitudes that hopefully I will explain. So the only final data we need is that not only is this quiver dynamics, is there any question? Oh, not only is this quiver dynamics giving us these peaks and dips, but assigned to this peak and dip, we can associate vectors also for every such walk. So the same table, wherever you see a peak, you put so I'm defining for every walk, we have a set of vectors. So it's the same table except that I am going to give some discrete integers. So we have, and so these are called G vectors. And so for every walk, I'm going to assign a vector, which can be directly read off from that table there. So for 1, 3, wherever there is a peak, you put +1. If there was a dip, you put -1. If there is nothing, you put 0. And similarly, other ones. So G14 is, and so on and so forth. I'll just write one more. G24 is -1, 1, 0. But of course, there are three. This is, of course, as you can see, these vectors are in 3-dimensional space. So these vectors are all spanning some 3-dimensional space, R3. And it turns out that there is a natural identification of the Cartesian basis with 3 of these vectors. And those are precisely the walks which are labeled by these dots. And this is always going to be true. So the fact that we started with a specific quiver picked out a specific choice of basis. As we will see later, the physics basis won't matter. And this is actually related to Johannes' question in Melissa's talk about the choice of basis that we will come to later. So then that means that I have these 3 G vectors, G13, G14, G15, and all other vectors are realized in this 3-dimensional space as linear combination. So G24 is just G24 is just in this. This is G24. But you can of course we can write all of them. And it turns out that this is a property of these G vectors. They always they are such that if you look at the space spanned by them, it is always the full R3. So here, if you look at G13, G14, G15, it is only spanning so if you say that I only want to look at the positive span of G13, G14, G15, so it's spanning only the positive part of the quadrant, like 1 quadrant out of 8. But if you look at all possible such sets of compatible walks, they always chart out a cone. And the union of the cone is full R3. So let me just recall, this is something we did last for the n equal to 5 explicitly. So I'll just quickly tell you what it is. Here it's hard for me to draw. So if I did the same thing for for n equal to 5, then you could easily check that all the G vectors look like this is G13, this is G14. It would turn out that this turns out to be G24, I think. Or not, this is G24. This is G25, and this is G35. And you see that, so every, if you look at a positive span of any of these 2 vectors, they always chart out a cone. And precisely the 2 paths which are compatible walks, this is from the last lecture, so please ask if something is not clear. So you see that 1, 3, 1, 4 were compatible walks, they chart out this cone. 1, 4, this should not be, I apologize, this should be 2, 4, sorry about it. 1, 4, 2, 4 are compatible, they chart out a cone. 2, 4, 2, 5 are compatible, they chart out a cone. 2, 5, 3, 5 are compatible, and 3, 5, 1, 3 are compatible. So, and the union of all the cones is full R2. And this always happens. So the generic statement is that, so let me just write some fact that starting with, so n bound quiver, so n hollow vertices generates a set of n into n minus 3 by 2 G vectors, which split this Cartesian space into cones, such that each cone is spanned by set of compatible G vectors, where IJs are the compatible walks. So I'm sorry, this is a mouthful, but this is just stating what we are seeing in these two examples. So maybe I'll give you a minute to just look at it, and if you have some question, you can ask. Correct, because 1, 4, 2, 5 are, yeah, not.
Here, in this case, it seems like all of these are
No, which one?
in the R3.
No, R3, because there'll be many more. I'm not drawing 3D, right? So there'll be like complicated 3D cones. Always the cone, there'll always be adjacent cones which are spanned by 3-dimensional cones spanned by only compatible walks. You can just take my word for it. So it's hard for me to draw. That's why it's here. It's very easy to see. So any wrong statement, Melissa will correct me. But so yeah. Where? G1 and G1 are certainly compatible. So the vectors are not, it's not a question of vectors being compatible, right? It's a question of 3 vectors which chart a cone are always going to be adjacent to each other, which are compatible walks. So if you have n equal to 6, that means you have every set of 3 walks are compatible. So 1, 3, 1, 4, 1, 5 are compatible, like that. And so if you draw the G vectors of these 3, they chart out cones, individual cones, so that the union of cones is R3. So cone means positive, of course, positive span, right? Like here, like G1, when I'm saying cone, I mean, I only look at the positive linear combination of 1, 3, 1, 4, etc. Shruti, ever?
Yeah, so this G vector fan is when you've chosen these triangulation 1, 3, 1.
Exactly, we could do it for any, yes.
That would change the way that you drew this.
Exactly. That's an excellent point. So sorry, yeah, exactly. So just let me, maybe I just draw it here. So for example, we could look at, we could look at the following. So this quiver is just something that we are, we just started with as an example where Shruti is saying this is, of course, there's nothing unique about it. The only thing unique is that we have 6 hollow dots and 3 solid dots. And then you could also have the following quiver, which is, then this is, let me draw it with triangulation. Sorry, I always get confused to draw it. I will delete the edges after I draw it. So this is an example of a quiver which is not of that type. So this is one. So here you would see that this one, this vertex will get labeled by 1, 3 in the sense the only walk which is a peak here. This will be by right 3, 5 and 1, 5. And the advantage of looking at it this way is that, okay, this is just an aside comment that this people who are interested in representation theory of cluster algebras, that these are called cyclic quivers, and somehow they are not, they don't naturally arise in cluster algebras. So the idea that could we get some Associahedra from here, this generalization which was done by the 4 authors I mentioned last time is more powerful in that sense, that you could start with any quiver like this. It doesn't have to be like this. These don't have to be linear, and you would still get nice Associahedra characterization. But so the algorithm is exactly the same. You don't have to. There's no new subtlety. Take all this orientation, peak, dip, etc., and you just. So now the point is that now we have these G vectors, and what these G vectors give us is a canonical drawing of this Associahedra, for example, in a Cartesian space. So again, this Cartesian space right now has no relation with physics at all. It's just an abstract Cartesian space. But we can now ask the following question. Maybe I come here. Is there a I am not being mathematically very precise because I am not a mathematician, but think if there's a more nuanced question, then we can ask Marisa. Is there a polytopic realization? So this is a question we want to ask of first I'm doing it for Associahedra, then we will see what happens in the case of generic accordiohedras of an Associahedron an minus 3 such that normals vectors to all facets which are codimension 1 faces are G vectors. So you may worry what is the connection of the facets with G vectors, and it is immediately clear by looking at the n equal to 5 example again. So in the n equal to 5 case, the Associahedra itself was a pentagon. As Ashok pointed out that there was a scope of confusion with the abstract pentagon and this one. So let me draw the Associahedron like this, where every vertex is labeled by a triangulation of a 5-gon. So for example, 1, 3, 1, 4, 1, 3, 3, 5, like that, 2, 5, 3, 5. So you see that the common element between any two adjacent vertices is precisely here, in this case, one chord, which is 1, 3. And this Associahedra is 2-dimension, and this is a codimension 1 face of the Associahedra, which is labeled by one chord. And this is true for in any dimension, that if you take just one chord, so you start with a triangulation in n equal to 6. And you ask, what does this one, so we know that the corresponding Associahedra is 3-dimensional. You can ask, what does one of these chords label? It labels a 2-dimensional face or a codimensional 1 face. This is just combinatoric, so you can just check it. And so which means that with every of this face we are assigning a G vector abstractly. G13, G14, G1, G35, etc. And now the question we are asking is there a polytope I can draw such that the normal to these faces are precisely the corresponding G vectors? Is the question clear? And so that means that I want to find out, yeah, so this is the question. I mean, there is a probably more precise way to write it. So, but for now, I think this is sufficient. And the answer that was given by ABHY first, which is yeah. And later this was in some sense crystallized by and the 4 P's that we saw last time is a very remarkably simple formula. The remarkably simple answer to this question, and the answer is the following. So we have all our G vectors span this 3-dimensional cone, right? So they all live in 3-dimensional cone, and so we want to, in this case, let's say in the case of n equal to 6, oh sorry, here n equal to 6. So I want to find a 3-dimensional polytope whose normal to the faces are precisely the G vectors. That's the goal I have. So let me label the axis as some Cartesian coordinates. So I could label it as x, y, z, but clearly every axis gets labeled by one G vector. So I'm labeling the axis also with the label 1, 4. But it's just a label, so it doesn't matter. I mean, it's so the only thing I'm saying is that once you start with one quiver, as Shruti was asking, in this, yeah. Precisely. No, they are not orthogonal. Because they are absolutely not orthogonal, because they are more than the one that their linearity space. So you see in this case, there are 5 G vectors. They all live in a 2-dimensional plane. They are never orthogonal. But always like so in this case, 2 of them are orthogonal, and they precisely correspond to the G vectors which came from these black dots, these solid dots, representative dots here. But if I change the basis as Shruti was asking, then the basis will be labeled by these three. Like in this case, G13, G35, G15.
Sorry, I'm getting a little confused about it. Seems like the data you started with was just some combinatoric data.
Yes.
And so how did you draw this? So can you just remind me again, how did you get these geometry vectors?
Yeah. So we just said, made the label that take a walk. Wherever you see a peak, there are, so because there are only three solid dots. So we have three components of the vectors that I'm writing down. So take a walk 1, 3. Wherever there's a peak, you put +1, dip -1, no, nothing, 0.
Oh, I see.
So you get three-dimensional space. So the number of such chords are n into n minus 3 by 2. Okay? And they all lie in R3. They all lie in, so just to, so the number of such chords are n into n minus 3 by 2. But clearly they lie in the dimensionality of the space is the number of black dots, which is n minus 3 only. So this number of columns is n minus 3. So we get so we get these G vectors which split Rn minus 3 into cones.
Okay, fine. I understood. Now the question there is there point of realization with Associahedron so that these G vectors are normals to the basis.
Yeah.
Now the Associahedron though didn't seem to have any geometric data about how you could draw it. It only had some data.
Absolutely, and there were many different realizations. In fact, because Associahedron is an old object, and in fact, so the idea was that can you, for any dimension n, can you consistently draw the Associahedron as a convex geometry? And there is no unique way to draw it. There are many different realizations, but this is a realization which completely comes from the geometric data. It only comes from these G vector assignments. So I'm asking a particular drawing which takes into account the fact that G vectors should give me the norm. The geometry should be induced by G vectors. So the previous drawings, the previous realization that came, as far as I know, they came from beautiful analysis of finding correct barycentric coordinates, but it was not related to G vectors.
It's a lot so structured to the Associahedron. Like if you had drawn it earlier, I could have deformed the Associahedron a little bit, and it would not have changed any of the combinatoric data.
And we will see that the deformation will be important for us. Right now we are starting with one realization mathematicians have given us. We will see what it gives us in physics.
Maybe something.
So we don't want to add any other information except what quivers are giving us. To me, this seems like the most minimal thing we have because the G vectors are coming from no other. It's just from the quiver dynamics, right? What is peak and dip?
Yeah. I meant the Associahedron you could have drawn.
Yeah, so your Associahedron is a geometry we can draw in so many ways now. No, absolutely. I completely agree.
You ask this question, you are introducing.
Exactly. And that you can ask why. This is led to Johannes' question also about the basis. And we will see what happens if we change the basis. Yeah, I agree. I mean, we have a very partial answer to that question, but we have some interesting, I think, interesting understanding now. Okay, and so actually the answer of this is extremely simple, and the answer is simply coming from the following realization. So let's say we have n minus 3 black dots. So the space in which we are having these G vectors is Rn minus 3, and say let's say we label this with some x13. So I'm choosing the specific quiver that Shruti asked me about, so that the basis vectors are G13, G14. This is just an example, right? You could have anything else also. X1, n minus 1. I think, yeah. Okay, so this is my Cartesian coordinates, which are all lying in the, is my counting correct? I think it n minus. Yeah, I guess it's okay, right? And yeah, I think it's correct. Yeah, x1 n minus 1. So that's my labeling of the coordinates. And now I want to ask, what's the polytopic realization of the Associahedra such that all the G vectors are normal to the codimension 1 faces? And the answer comes as follows. So let me just define something which is Yij, which is defined as so remember that this space is part of a much larger space, because the space we are really starting with is space of all chords, which has many more coordinates. So we have x13, x14, x24, x1 n minus 1. Right? Please ask me if something is not clear. So just as an example, if you have n equal to 5, then the full space was of course R5, because it's labeled by following coordinates. Yeah. But as we saw that if you choose the specific quiver, then the linearity space for the cones is exactly only this R2 which is spanned by x13, x14. So I hope this distinction is clear. We always have a space which is bigger and in which the cones, the G vectors span out a cone which is a subspace. So now let me define for any ij, let me define a new coordinate which is some linear combination. So it's just xi minus 1 j plus 1 plus xi minus 1j plus xij minus 1 minus xij minus x. It's just a rewriting of my coordinate labels just to show the result in a simpler form. And what this beautiful analysis told us is that the answer to this question is the following set of equations. Consider yij equal to minus, I will explain the notation, Cij for all ij which are not in okay, I have to explain. There are many new notation I have to explain. So, first let me explain what the equations are. So, take this Yij for all ij and write these equations Yij equal to minus some arbitrary positive constants. All theCijs are positive. But not for all ij's, of course, for only those ij's which are not so we are starting with this as the reference G vectors, right? So these reference G vectors, if I draw as part of my n-gon, it is 1, 3, 1, 4, 1 n minus 1. Look at all the chords you obtain by rigidly rotating this once counterclockwise. So look at all the chords which are basically ending in n as opposed to 1. So I could have actually done that. So 2n, 3n, like that. Write this equation out for all chords except these chords. Is a statement clear? We'll do an example, then it will be more clear. So write this set of equation for all chords, internal chords, except those chords which are one counterclockwise flip away from what you started with. Okay, and these are called ABHY equations. And as Suvrat is asking, and Shruti was also emphasizing, we must remember that this realization depends on this reference quiver that we are starting with. So for every change of the quiver, we get new realization of the Associahedron. But you can show that if you chart out these equations, so if you look at solution to these equations in x13 ... x1n minus 1 greater than or equal to 0 in this positive quadrant, then you get a convex realization of the Associahedron. So this is the first result that we will use. I'll give an example so it will be clear what this means. So let's do one example in n equal to 5 case. And it's really the equations are really like quite simple in this sense. It's just this algorithm. So let's do n equal to 5 example very explicitly. So the full space we are starting with is R5. And if I use that fixed quiver, then my linearity space is spanned by x13, x14. And so I want to write this equation Yij equal to minus Cij for all ij which are not in this set 2, 5 and 3, 5. Which means I have 3 equations because I am removing 2, total number of chords are 5. I am writing this equation for everything except 2 chords. So I have 3 equations, and those equations are y13 is minus c13, y24 is minus c24, and y14 is minus c14. Just to remind you, all the c's have nothing to do with each other except they are all positive. And now what you do is you solve these equations. So remember, yij's are in terms of, so y13 is y13 is we can in terms of xij's, as you can see. So there are 5 variables and there are 3 equations. So we can solve for x24, x25, x35 in terms of the variables that we are our Cartesian basis. And that basically gives us the following drawing. It's just linear equation, so you can immediately solve it, and you get this particular realization of a two-dimensional associahedron, where this boundary corresponds to x14 equal to 0. Of course, that's obvious. This one is x13 equal to 0. This boundary is x35 equal to 0. You can check by equations when you solve these equations. This boundary is x25 equal to 0, and this boundary is x24 equal to 0. And intuitively, you can see that this is really the normals are the G vectors. The normal to these are the G vectors. So I can stop here and see if there's any question. Because this is basically the algorithm that you can use to draw them. No, there's no, right now there's no physics yet. No, zero, yes. Sorry. It doesn't belong to the C means one counterclockwise rotation of what we start with, the reference that we start with. So if you start with a reference 1314, the one flip is 2535. So you exclude 2535. That's the equation. Yeah. Okay, and so this basically gives us the constructive way to make ABHY associahedra, but depending on any choice of basis that you start with. So the Shruti basis that she asked about was not, so in n equal to, so just to complete this analysis, for n equal to 6, the full space of all chords is 9-dimensional, x13, x14, x15, x25, x35, and then there should be x26, x36, and x46. And in this, the basis that I was drawing was this one, because the G vectors were 1, 0, 0, 0, 1, 0, 0, 0, 1. But if we had chosen the quiver Shruti suggested, then the basis would have been x13, x35, and x15. And then I would draw the same equations with these in this quadrant, and then I would get a different realization of the ABHY associahedron. So is this part clear? So this is, we have as many realizations of associahedra as many compatible walk sets that we have, which is actually you can count, it's the Catalan number. So we have lots of ways to draw the associahedra just from this one, just from this set of quivers. Okay, but now this actually we get more, because as we saw that if you did this subquiver analysis, which I think I deleted, no, it's here. For example, in this concrete case, then if you focused on this quiver here, then combinatorially we got an accordiahedra, and now we can ask, okay, now that I have drawn an associahedra in this space, what about drawing this corresponding accordiahedra also in this space? And that answer is actually quite simple, and again comes from the G vectors. So maybe I delete this. So the basic upshot is that the quiver will give us convex way to draw all accordiahedra with the only premise that the normal to the faces should be the G vectors. That's it. So that's so in this case, for example, the G vectors are so the basis here. So the set of all chords which dissect, there are only 2 chords, and the basis is simply so if I write the G vectors, G14 is +1. Remember with the subquiver. So this is the number of points in the subquiver is 1. So the dimensionality of the space is 1. So G14 is +1 because there's a peak at 1,4, and G36 is -1. And so then this means that G14 is basically this, and G36 is this. And now you can ask, given these associahedra equations, can I use them to draw that particular accordiahedra? And that obtained by simply projecting this associahedra on that one-dimensional axis, which basically means in practical terms, take all your equations in n equal to 6 case, take all n equal to 6 ABHY equations, which are 6 equations in all, and look at equation which only involve x14 and x36. Only these two variables, no other variable. That turns out to be precisely one equation, and that equation turns out to be x14 plus x36. It's some linear algebra, so I cannot, of course, prove it. You have to work out the equation. But there's only one equation which you know only these two entries and nothing else. And that sum is some linear combination of C13, C14, something. I think it's this one. I'm not completely sure about it. But so this is what we call a projection. Again, because of lack of time, I'm not defining it in a rigorous way. The most rigorous analysis is by, if you want to understand it in full detail, then it's given in this paper in 2017, which are called geometric realizations of Accordia-Hydra, 2018, I think. Where they show that how any realization of Accordia-Hydra can be obtained by projections of this type from the Associahedron. So is this clear? So we got a specific, in the 1436 plane, we got a specific realization of our one-dimensional Accordia-Hydra like this. So we started with some three-dimensional Associahedra, which was in 131415 plane in the quadrant, and then when you project, you get actually it's a projection, and the projection sits in the 1436 plane, and it's this one. But you could do this for any Accordia-Hydra. So everything started from this equation. So these are basically master equations, and you then project them onto whatever your subquiver was. So this plus projection gives geometric realization of any Accordia-Hydra. All Accordia-Hydra. Okay. I wouldn't say it like that necessarily. I would just say that you can, I'm giving you again lowly physics way to do it. If you look at all the 6 equations and you add and subtract, you see that there's only one equation. You can rewrite the equations by some linear combination, which involve only these 2 entries. That's what I'm calling projection. There is a more nicer way to geometrically do it. I'm just not lack of time. I'm not doing it like that. But if you want the details, you should look at this paper. It's right in the end, one of the lemmas in this paper. Okay. I should mention that this was taught to me by one of my collaborators, Brunmai, because these papers are above my pay grade, but he was able to understand all these math papers and explain. Yeah, sorry, there was a question. So that's what it depends. So if you start with some specific subquiver like this one, okay. So now you see all the first what you will do from this analysis. You will see all the walks which have either a peak or a dip here and here, but not here. So you get many walks. We have Cartesian coordinate for each such walk, like x13, x14, let's say x24, etc. And now you look at your ABHY equations. Look at only those equations which you know only those x variables. That's the projection. So look at the equations which involve don't involve x15 and don't involve x46, don't involve x15 because it is a peak here, etc. No, but that's a projection. I mean, rearrange is just a way to compute for us, but it's the math result is a way to project the Associahedron onto Accordia-Hydra. So this rearrangement is, I'm telling, as a practical way to do this projection, but there is a formal theorem that we can do this. Yeah. Okay. Any questions so far? So now we have so far still not touched physics, but we have found from some abstract objects, some concrete geometric objects, which are a large class of polytopes. Yes.
This fan, the case of the Associahedron, it has like a straightforward relation to the dual, right?
Yeah.
Yes.
Yes.
Line is
Yes.
What about the Accordia-Hydron?
In general, it does. In 1D, the dual is always complicated, even for Associahedra. So, but in general, yeah, you could, of course, you could do a dual, which will be a simplicial complex always for all Accordia-Hydra. Yeah. Okay, thanks. Yeah. Now let me just say some properties of Associahedra, etc., which actually are also sort of very important of why these things get related to amplitudes. So these are just some. I will just state them because we cannot prove them, but by playing with example, at least you can see they are true. So let me just list down some key properties of n minus 3. So just as a convention, when I do it like this, I mean a combinatorial polytope. But now that we have drawn them, sometimes I will also do it like this. Which, or maybe I should do it like this. Where this tells us that you have to start with a reference quiver, and it gives us a particular drawing of the Associahedra. So although the combinatorial thing doesn't depend on any reference dissection, the drawings do depend on the reference dissection because they depend on that quiver that we started with. Because the normal vectors then otherwise get changed. So the key properties are, one property is that an minus 3 or all accordiahedra, not just Associahedra but also all accordiahedra, are what are called simple polytopes, which means that this simplicity simply means that the number of codimension 1 faces adjacent to a given vertex are equal to dimension of the polytope. So this is telling us that every vertex of a Associahedra is always adjacent to n minus 3 codimension 1 faces. So the reason this turns out to be, of course, relevant for physics is because every vertex is full set triangulation. So every vertex you can think of it as, again, right now we are not connected to Feynman diagram. I'm just giving an intuition of why I'm even bothering to discuss this property. If you take a particular Feynman diagram with 6 external vertices, so it has 3 propagators which correspond to which corresponds to a triangulation of a 6-gon, and this vertex is adjacent to 3 propagators. I mean, it contains 3 propagators, 1, 3, 1, 4, and 1, 5. And since each such 1, 3 is a codimension 1 phase, this is compatible with what we get in the Feynman diagram, that every full cut has these many partial cuts, which is like single cuts, which is n minus 3. So is that clear? I mean, that's the reason I stated it. Otherwise, you would think why is it even interesting from our perspective? And the other probably more crucial property is that there are 2 crucial properties. One, that any boundary, and this is not true for all accordiahedra. This was true for all accordiahedra also. So I stated it like this. But the property I'm stating now is not true for all accordiahedra. It's certainly true for Associahedra and a class of accordiahedra. But I'm just going to state it because of lack of time for the Associahedron, that any boundary of an minus 3 is always a product of lower dimensional Associahedra. M for m less than n minus 3. This property is actually very profound. It's not obvious at all, because this property is telling us that let's start building up the Associahedra combinatorially. So we know that 1-dimensional Associahedra is just a line which is labeled by, let's say, triangulation of a 4-gon. And as we saw, the 2-dimensional, so this is A1, A2 was a pentagon which was labeled by this triangulation, etc. If you look at A3, this property tells us that any codimension 1 face of A3 has to be either a pentagon or a square, which is product of line and a line. But there can be no codimension 1 boundary of A3 which is a hexagon. So it kind of really constrains the structure of the boundary of this Associahedra. So it's of course not true for generic polytopes, because in principle you could add boundaries which were hexagons, etc., say for a 3-dimensional polytope, but it will never happen here. And as we will see, I don't know if you will have time, that this property is related to the fact that amplitudes factorize into sub-amplitudes when we take cuts. So I'm just saying that the reason I'm stating some properties which play a role in the end when these things give us S matrices when we cut propagators. And of course, for a tree level amplitude, this property is related to locality. Unitarity, I apologize. And so you see that somehow, at least at some combinatorial level, the unitarity emerged simply from the way the boundaries are arranged of the Associahedron. So, you know, I mean, if you people who are aware of CHY formulation will not be very surprised by this, of course, but this is the reason why we even get something which has unitarity from these kind of geometries. And finally, last property, which as I think Johannes also said that I think next week will be covered in detail, is that all these accordiahedra, associahedra, they are very special case of a rich class of geometries which are called positive geometries. So let me just say that property 3, all accordiahedra. By the way, I mean even Associahedra is an accordiahedron, but it is a very special kind where the vertices are triangulations. So all accordiahedra, I mean including Associahedra, are examples, are positive geometries. And by positive geometry, there is a very nice mathematical definition, and I think Johannes told the reference, I think which is still state of the art by Nima and Bai and U. Thomas, where they really introduced this positive geometry, which in 2017. But again, from a physics perspective, and at least for our context, a positive geometry is any geometry which has boundary of all codimensions. So a counter example is a disk. This is not a positive geometry because it doesn't have, it of course has a boundary of codimension 1, but it doesn't have that codimension 2 boundary because it has no vertex as a boundary. So every polytope, every linear polytope is trivially a positive geometry. And because we are drawing these as convex polytopes, these accordiahedra are obviously in a trivial sense positive geometries. But the realization that they are positive geometries buys us a lot, as I will say in a minute. So these are 3 properties you should keep in mind for the property 2 is more subtle for generic accordiahedra, so I will not, if you want, I can tell you later, but property 1 and property 3 are true for all accordiahedra, and property 2 is valid for associahedra and some class of accordiahedra. So, is there any question about this?
You can take a one-dimensional boundary and also go to the edge, and so you get a two-dimensional. That's what you mean.
Codimension 2 boundary, you mean?
So you get a codimension. So what does that's a little confusing.
So every codimension, any codimension K boundary is always a product of lower dimensional associahedra. So that's why the example in the n equal to 6 case is interesting, that you cannot have a boundary which is neither a product of, you cannot have a 2-dimensional boundary which is not a product of a line and a line which is a square, or pentagon and a point which is a pentagon. You can never have a boundary which is hexagon, octagon, etc. But this is true if you go at higher n also, that the boundaries are always built out of lower dimensional associahedra.
If you look at the whole boundary, the point is at various points it degenerates into something.
You mean but boundary of all codimension? Yes.
The boundary of the whole
figure. You mean but it has codimension 1 and codimension 2 boundaries.
Yeah, so the full boundary is actually just the whole perimeter, right? And what you mean is degenerating into something which is singular.
Yeah, but I mean these properties I'm saying are really fixed for dimension by dimension of a boundary, right? Like a fixed codimension boundary is product of associahedra. It's true also, of course, for vertex is trivially true. It's product of a 0 dimension, but it's also true for all other codimension boundaries. Okay, you know how much time I have? Okay, so I will go. I will skip some things and go a little. I'm very sorry about this, that we barely ran out of time before starting to discuss physics. But okay, so I skipped some details at least. Now the reason I stated these properties, the first two, of course, as we discussed, why they are related to physics. The reason this property I'm even stating is because all positive geometries, no matter how complicated they are defined in terms of some, the rigorous definition involves some algebraic geometry input, but whatever they are, they have a beautiful fundamental property that any positive geometry, which is some real geometry, I mean, it's some convex space in some real Rn basically. Any positive geometry has a canonical form. This is very much tied to what Melissa explained to us. A top canonical form. So whatever is the dimension of positive geometry, there is a top canonical form and is unique up to plus or minus 1, just one sign, which is like an overall orientation. And this form is unique because it satisfies the following property, that it has property 1, that it has simple poles on all the boundaries and nowhere else of the positive geometry. So maybe I should call positive geometry something, let me call it P. So of P. So remember, P is some closed convex geometry which has boundary of all codimension, and you can just keep in mind Associahedron, which is like a linear polytope which has boundary of all codimension. So the fact that it's a positive geometry, you can use it to show that it has a unique top form. The form is the same dimension as the dimension of the geometry, which has simple poles on all the boundaries and only on the boundaries. And the way to compute residues is the following. If B is a boundary of P and H is some hyperplane in, so this is a positive geometry P. I'm just right now writing it has a dimension mod P. So draw this in this R mod P and take a boundary. So let's say in the Associahedron case, take this boundary. Then of course this is part of this hyperplane. Then the residue of the form of so there is a canonical form that's called, this is my P. There is a canonical form which I define on all of the space, which is omega P. And this form is such that if I look at this particular boundary, remember a boundary of a positive geometry, sorry, I should have said it is also a positive geometry, because of course if the positive geometry has boundaries of all codimension, any of its boundary also has boundaries of all codimension. So if I take this B, it's also a positive geometry, and omega of B is simply a residue on H of omega of P. So there is a consistent gluing of these forms from that you can use to construct these forms, which are fixed then up to a sign. So let me just give you the concrete expression for what the form is for Associahedron, and that's basically the get us somewhere at least into the physics. So we can use these results and show that given a specific realization of the Associahedron, where we had to fix this specific quiver. So I'm always fixing this quiver just because we saw this example. In this case, in there's a unique form omega, which is a top form, so it has dimension n minus 3. This form is defined on the full space, so it's defined on R n into n minus 3 by 2, and the form is precisely equal to summation over all the. So now I'm going slightly fast, so if something is not clear, please ask. Remember that every set of compatible works with a triangulation. So you sum over all triangulation because every vertex of Associahedron was labeled by a triangulation. Then you fix one triangulation and call it like my reference, like this one. That's why I'm using the reference. And then when you start going to other triangulation, you start flipping. So if you go to T from here by even number of flips, you put +1, odd number of flips -1. So that I'm denoting like this. This mod T doesn't mean number of chords. It means how many steps you took to go from this to this T times D wedge D log Xij, where the chord Ij is in T. Okay, so the positive geometry understanding of Associahedra, ABHY Associahedra, for any realization gives us this particular canonical form, which is defined on the ambient space in which our Associahedron is realized. So now and this is fixed up to a sign, I mean up to an overall sign. And now the point is that, let me just schematically now draw the picture. So I have some Rn into n minus 3 by 2, and I have some positive geometry sitting. And this positive geometry, an minus 3, gave us some form. And now what you can do is, of course, you can pull back this form on the geometry because this is described by some linear equations. So you can evaluate this form on this geometry. And when you do that, it's very simple to show in this case that the evaluation of the form on this, any realization of Associahedron, which is given by these G vectors. So now this will play an important role. So you take your form and you pull it back onto your an minus 3, which was in a specific, drawn in a specific basis, and then you can show that this is equal to sorry. Okay, so this is the result, and the basis we chose played a role here. This is also related to Johannes' question, where I'll come back in a minute. So there is a basis dependence, and what is remarkable is that there were these minus signs here, but when you pull it back onto the Associahedra, you can use the equations, and all the minus signs sort of go away. You get like a positive sum over all these products of the x chords. So remember that each product is over, each T is same as vertex of Associahedron. So it's product over all the vertices. And this is fixed by our quiver. So the quiver information is not forgotten. It remains in this in the form itself that we write down. Let me just quickly say that now that we have this projection, if you have a projection of one geometry onto the other, you would also project the form. And if you did this projection, for example, for n equal to 6 for the Arkani-Hydra we had, which was this one, then it turns out that the form n minus 3 projected, so I'm just doing it like this, onto this Arkani-Hydra turns out to be okay. So this is for one example. So what has this told us? This has told us that your quiver has given us a top form. It has given us some convex realization of Associahedra, and it has given us all Arkani-Hydra as projections. And then we have unique forms on each of them because all of these are positive geometries. So is this at least if I run out of time after this, at least at this point you can stop me and see if it's clear, because this is one of the main inputs of everything that happens later. Yeah. Yeah, so this formula, let me give you an intuition, because unfortunately I don't have time of why this minus comes. Minus comes because of a key property of the positive geometry. So let me just give an example that, so this is a positive geometry. Okay, and let's say that in one dimension, let's say this is sitting at some point A and sitting at a point B. Then you see that I want to define a form which is simple poles here and nowhere else. Precisely. That's why the minus sign comes, exactly. Yes.
I'm not sure I follow how many of those belong formulas there.
As many as the, so you mean So there are n minus 3 entries in each of these, right? Because there are n minus 3 chords which triangulate. So it's an n minus 3 form, it's a top form on the associahedron. So it's an n minus 3 form. And the number of terms are number of vertices, which is actually a Catalan number. So it's a lot of, it's as many Feynman diagrams in phi cube, planar phi cube theory that you would have.
But then why do you sort of bring in this, the dimension of the ambient space?
No, I didn't bring in anything because this is a form in the ambient space because right now these x are independent coordinates in the ambient space. Yeah. So it's only when I pull back to associahedra it gets pulled back. So it's a form which has the same dimension as associahedra, but it lives in the ambient space.
And that's pulled on already on the associahedra, right?
This is not on associahedra. This is a form in the ambient space. When I pull it back, I get this. This is the pullback on the associahedron. Okay, maybe I should move on. And so let me just say now what is the, just quickly in 2 minutes, I will tell you what the relation of physics is. I'll just give you 2 examples. So far we have not made any connection of these x variables with any physics variables. But if you now remember, we had a basis, xij basis, which we introduced in the previous discussion, which was defined as pi plus dot 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 pj minus 1 square for all I mean 1 less than I, less than j, n minus 1, something like that. And this number of these bases were also n into n minus 3 by 2. And so now we have the following picture. We have this abstract Cartesian space in which all the quiver dynamics is going on. And so we have some an minus 3. We could have some projection onto Arkani-Hahedra. And we have a form. We have a form omega, which is pulled back, which is this form. So this T refers to the reference. So that is that 1, 3 to 1 n minus 1. That form will also get projected, and we would get a form on the Arkani-Hahedra. And now we have this other space, which is the kinematic space, which is also of same dimension, of course.
Sorry, Alok. Maybe it's best not to use the last.
Oh, sorry.
Camera can't
Yes.
follow you.
Yes. Sorry about that. Yeah, this is our kinematic space, which is also labeled. So this is labeled by xij's. This is what we did, and this is labeled by xij. And now we can ask, okay, so once I'm given the structures, what would happen if I start mapping these spaces to these spaces? And the obvious map that you would start with is just identify. So just say that my xij, this is one example, is equal to xij. So this is like a linear identity diffeomorphism between a space in which mathematicians gave us some beautiful structures and the kinematic space. And then it turns out everything remains the same, except everywhere you see small x, you put capital X. And here, this one. And now it turns out that this particular quantity is the tree-level amplitude, n-particle tree-level amplitude for phi cube color-ordered theory. So if you don't know if you have not heard of this color ordering, it's okay. I think that Johannes introduced it anyway in the construct of Young-Mills, so it's similar for the scalars. And so this is precisely that amplitude where the ordering is fixed to be 1 to n. Yeah, so because of lack of time. So the form has a basis. This is related to exactly what Melissa said. So I'll come to the basis, the basis change now. But whatever is this rational function multiplying it. Now you can ask, can I invariantly understand what this is? And this particular thing is a volume of this associahedron as a dual. And if you compute its volume in a specific way, that's precisely equal to this. The form disappears. No. This itself is a volume of some dual, but I can tell you in person. I mean, but right now the point is whatever is the rational function is what is producing first the amplitude. If you do this identification right now, I'll just in 1 minute, I'll give you one more example where this is not true. And in this case, you can ask, okay, what about this one? And it turns out this is also amplitude for a theory. So it's a 6-point amplitude for phi 4 theory. But because the scalar has colors, the 2 colors should be different. So if you consider the following 2 colorings, phi 4. So this particular thing, just these two terms, is a specific color ordered 6-point amplitude for a 5-4 theory, which has some ordering. So the reason I'm saying this is that I'm just producing some very limited data that they are always producing some amplitudes for some theories. They are not our garden variety theories. These are some maybe exotic theories, but they are theories. They are local quantum field theories. Let me just take one more minute to say what if I don't do this trivial identification. And let me give you one example of one identification, which is not this. So let's say that let us say that I said I write my xij is equal to some alpha, some positive constant times xij for all ij. Sorry. Yeah. Oh, there's too much chalk. Okay. Can I use color then? Okay. Sorry, I'll just take one more minute. So let me just now give a different map, which is say xij is equal to alpha. Thank you, Suvrat. So in general, we can look at a slightly simpler. Okay, then I go a bit slow. So of course you could say, let me look at following type of maps, which is small xij is equal to alpha ij, capital Xij plus beta ij. These are also not very special maps, where alphas and betas are some positive constant, let's say. Okay, so these are some diagonal linear diffeomorphisms between the math Cartesian space and the kinematic space. And of course, then a natural question to ask is, for generic choice of alpha and beta, if I write down this pullback of these forms, do they give us amplitudes for anything? And then it turns out so far, all examples we look at, we are always able to cook up some Lagrangian. So let me give one example, which is a nice one actually, which is that you take Xij to be alpha ij xij minus m square for all ij such that mod j minus I is 2 modulo n, and xij is equal to xij minus m square for all for the complementary set. For ij not in the set S. So let me call this a set S. Now you take this. Actually, let me put it as alpha, same alpha as simplicity. So the point is that if you have x13, then you have alpha x13 minus m square. So in n equal to 6, what this diffeomorphism is telling me is that x13 is alpha x13 minus m square, but x14 is simply x14 minus m square. And now if you do this, if you take this diffeomorphism and you pull it back onto this, you have a space Rn into n minus 3/2, and now we have a diffeomorphism, very trivial diffeomorphism. Let me call it 5 into Kn. So now I can push forward this differential form and see what I find, and what we find is the following. So we can write a more general formula. I'm giving the example for n equal to 6. So in n equal to 6, we see that for n equal to 6, we get alpha by sorry 1 by alpha. Sorry, 1 second. I'll just plus all the other terms multiplied with and now you can ask, okay, what is this garbage? And you can show that this is same as a 6-point amplitude for a theory where the Lagrangian is, the interaction term is, let's say, lambda 1 phi 1 cube plus lambda 2 phi 2 cube, plus lambda 3 phi 1 square phi 2, where phi 1 is massless and phi 2 has a mass m. And now if you compute amplitude where external particles are all phi 1 particles, you can notice why there are precisely two terms that would differ, because you have if you have a diagram like this with this Lagrangian, let me just draw and then color something. Then you see that because my interactions are such that if my all external particles are phi 1 which are massless, then because I don't have a self coupling for phi 1, I have to have only massive propagators. So this is one example where every coupling is either, so this coupling is lambda, oh sorry, it's lambda 1 phi 1 phi 2 square. And so this one is lambda 3, this one is lambda 1, and lambda 3. That's this coupling, but you notice that if I look at this diagram, which is also part of this 6-point amplitude computation, then this is lambda 3, lambda 3, lambda 3, but this one is lambda 2. And so you notice that if you can now compute and you can show, I think, that if you identify alpha with lambda 3, lambda 1 by lambda 2 square, I think, something like that, then this is precisely the 6-point amplitude for this Lagrangian, where all the external particles are massless. And you can generalize this to any n. You can write this result for any n. So it was just one illustration that. Say that again?
3-point amplitude as lambda 2 and lambda
3
3 and lambda
point.
for this Lagrangian.
Yes.
So let's say I just want to get the 3-point amplitude, not the 5-point, not the 6-point amplitude.
3-point is just a vertex, no? It's just a zero-dimensional Associahedron, yeah.
So the zero-dimensional Associahedron, I can see there are 3 different kinds of them.
Exactly.
And there is lambda and lambda. How do I see that?
You see that? I just didn't have time. So you can ask, okay, this form, did it come from the original Associahedron? And because when I do this map, remember I have a convex relation of Associahedron. When I'm mapping it, if I use it, it becomes a deformed, because some of the linear equations get modified. So the shape of the Associahedron changed. So that change of shape is why the pullback of the form changed, and that form pullback gave me this particular. So this was a little bit, at least this is a very primitive example, but slightly related to Johannes' question, that if I change basis with a non-trivial between what is the abstract space in which all these polytopes are sitting and the kinematic space, even a simplest map like this gives us amplitude of a different theory. This is clearly unitarily different theory because they have different spectrum. They are two particles with different masses. And so, no, the species means right now, you see, that's what I'm saying, that is only able to compute right now this example of this map where all the external particles are massless. It's only computing that. They're phi 1, they're only phi 1, yeah. So the logic here is I'm not looking for a specific theory, because that we can do that, of course, and we did that for some examples. But right now the logic was that we want to know if I take some diffeomorphisms, which is not an input from the quiver theory or anything, do I generate amplitudes or not? And I'm just telling you why even these maps give us some amplitude in some class of theories. These are not all amplitudes in these theories. Yeah.
Phi 1 particles, and I'm allowed to introduce as many other fields as I like, as auxiliary fields.
Yes.
But they never enter in external states.
Yes.
Is there any restriction on the kinds of polynomials I can, or functions I can get in scattering
For tree,
amplitudes?
for tree level, no, I don't think so. I mean, in the sense that you could, yeah, I mean, we looked at more general maps, which were, where there were the alpha betas were generic, and we found polynomial interaction with different masses, but these are tree level amplitudes. I don't
No,
think
no,
it's
I'm
very
asking a different
fundamental.
question. Let's say I'll do Feynman diagrams. I do the conventional
Yeah.
approach.
Yeah.
And I just allow, that I just take external particles to be phi1. It's a very simple question. Maybe.
Yeah,
it's
no,
just
no,
a-
yeah.
And I allow phi1 to interact with other fields.
Yes.
With all possible ways. But the
Yes.
other fields I never consider in external states.
Okay.
Is there any constraints on the kinds of tree level S matrices I can get? Or can I get basically anything I like by introducing lots of intermediate fields? And which
So
will-
right now we are only getting scalar, because we are never, remember, whatever linear map we do, we never
get
generate
this.
numerator
Fine,
factors.
fine. Okay, so let's
so
do
they are not
scalar.
derivative. Although now I don't have time, because a beautiful, this is a very primitive example, but a beautiful result of Nima and Song and others is that there is a, then I come back to your question, that there are specific these linear maps, they're very clever, such that if you do an expansion in this, so they're almost like this, except that the details of how this shift is happening is changing. There is no alpha for them. There are some MIJs for them. And if you do expansion in MIJs, you get nonlinear sigma model, you generate derivative interactions in the large M limit, I think. So you can get much more sophisticated theories via these diffeomorphisms amplitudes. Those are the ones where you get derivative interactions by some expansion. But in general, these maps don't give you numerator factors. They just give you this. Okay, now you ask.
Question is, so if I only look at these kinds of things that look like 1 by function of Mandelstam plus beta,
Correct.
what are the it seems like you could get a very wide class of functions just by taking phi1 and coupling it, just even in the Feynman diagram approach.
Correct.
So is it surprising then that by doing these kinds of arbitrary maps that you are able to find some theory that cook up some theory that gives you the same answer? Because the set of all theories might already be giving you almost a very large class of answers.
Yeah, the point is that Associahedron has
Yeah,
this structure, and also it should not have happened without the form, by the way. This shift, the alpha adjustment really happened because this one has, there are some alphas here. So it's the form that tells us that this got related. At the level of just function, we would not have seen it also.
I see. Yeah, by the way, unitarity, the point was, of course, unitarity you're not imposing because you're never seeing the phi2 in cuts. So if you saw phi2 in cuts, then you would impose unitarity. But if you only have phi1, then unitarity is not a very strong statement. That's what I'm worried about here. But maybe.
No, but the unitarity is I mean, for a tree level particular amplitude, unitarity imposes some constraint, which is a factor in sub amplitude.
No,
so
but you're not seeing it, no, because you can't see phi2 in external particles.
Yeah. So here, because I give you
see-
example, like I can cook. You are right, absolutely correct. So if in our paper we have done a more detailed analysis of how to include the sub amplitude with external. It's just lack of time. I'm not putting that. There is a way to consistently get unitarity in the sense of the sub amplitudes having external phi2 particles. So I just, as an example, I just told you that this map gives us this class of amplitudes. Yeah, I mean, yeah.
That the terms we are getting here are in one-to-one correspondence with Feynman graphs.
For the planar, I mean, for color ordered amplitudes. Yeah.
So planar graphs, which is color ordered, just gives you planar.
Because it's cubic means Catalan number of Feynman diagrams of a Catalan number, which is number of vertices of the Associahedron. So that's not a,
so
that is just counting.
Really just giving you one-to-one correspondence with, it's not summing up multiple Feynman graphs into one in any way.
No, it's not doing that, no. But one could, even at tree level, there is a way to compute this because, I mean, this is something that Melissa also talked about a little bit, that this is related to this Hodges construction, that this thing is volume of some dual of Associahedron. And once you realize this is a volume, you can compute volume in terms of simplices, sum of simplices. And you see that, let's say you want to compute 5 particle phi cube amplitude. The usual Feynman diagram is like 5, you sum over 5 triangles. But then you could have looked at coarse volumes, which are some over 3 triangles. So already at this level, you see that there's a possibility of more efficient computations, because of the fact that you can split a geometric object in different ways. And Feynman diagrammatic splitting is not the most efficient one you already see here, or even in these trivial, relatively trivial examples. So I can just draw a picture. So the dual, let me just draw schematically. I mean, just without going into formula. So this is my Associahedron, and the dual of the Associahedron is this thing. And now so what turns out is this quantity, I mean, forget this alpha, is like a volume of this in some specific way when you, And now to compute volume, you can do it in many ways. So you could do it like this. So it's sum over 1, 2, 3, 4, 5 triangles. But you could also compute this volume by splitting it simply into 3 triangles. The previous split is the Feynman diagrammatic. This is, so clearly in some, I mean, this is a simpler computation. It's just rearrangement of Feynman terms. It's not something new, but already you see a potential why this could lead to more efficient way to compute them. No, I did not write this as a dual volume. No, I did not write that. Yeah. Sorry, I could not go into one loop, but just want to say that pretty much everything I have said, I would say almost without exception, goes through for one loop integrand for phi to the p theories. We haven't extensively studied these deformations of this type, except we have some few examples that we looked at, but there's a lot more that we have to understand that give us loop integrands for generic scalar theories. So, yeah. Even this projections into Arkani-Hedra gives you polytopes for like one loop phi 4 and phi p integrands. I can tell you more detail if you're interested, but maybe let me just stop. Actually, Ashok has a.
It's a good moment to thank.
Oh, thanks. Sorry for going over time.
Indeed, thank you again for very interactive lectures. And indeed, in that spirit, we already have some discussion. So, and I think we have more time if people have more questions. As usual,
Ashok has a.
yes, please use the microphone. Yeah.
I just wanted to clarify exactly what is the statement. So take this theory of two scalars, and suppose both are massless.
Yes.
So is it claimed that any amplitude, any tree amplitude in that theory is obtained from Associahedron? Or you have
My statement is, I would not be able to prove it, but my statement is that there is a deformation of Associahedron. If there is no derivative interaction, I would be able to obtain it.
I see.
Yeah.
And this generalizes to multiple scalars?
Yeah. So I mean that's at least again we don't have any rigorous proofs, but we just played around with these maps. I mean these are really diagonal maps also. We are not even mixing these IJ. They are not even GLN transformations. They are identity, but diagonals are not identity. I mean these alphas can be, and we got some amplitudes for n particles which were multiple scalar field with different masses interacting with different couplings, etc. And the couplings, relative couplings were constrained by this, how many parameters we had in these deformation maps.
Yeah, but I think I'm asking the reverse question, not that given an Associahedron, you try to deformation, you try to associate a Lagrangian.
Yes.
But suppose I give a Lagrangian.
Yeah, it's very hard. I mean, it's very difficult. We haven't. If you give me a Lagrangian, ask, okay, you compute a tree level amplitude up to some ordering coupling. There are many cases that I tried, but I have not succeeded yet. That seems to be a harder question. The only one we have been able to answer is if you look at uncolored scalar, like you look at full normal phi cube theory, which is U channel also, then that's also not very trivial, but it's a nice compact expression that you could just look at some maps coming from some cosets of permutation groups in this case, and that gives you. So what happens is that this Associahedron that we have for say n equal to 4 was like this because it was. This ABHY Associahedron is like this. This is my 1, 3, and this is my 2, 4 axis, x1, 3 and x2, 4 axis. Then if you look at the specific action of some permutation group, you get two more, two deformed realizations of the ABHY Associahedron. And the sum over the forms of this is like twice 1 by S plus 1 by T plus 1 by U. And it turns out that this, of course, because of the Bose symmetry of Feynman diagrams, even for an n particle, you can check that the final answer is 2 to the n minus 3 times you sum over some specific permutation group and look at this canonical form, push forward under this permutation group of the Associahedron. So you get your ABHY Associahedron gets realized in many different regimes of a kinematic space, and the sum gives you up to a multiplicative factor, which is just this, like uncolored phi cube amplitude. I mean, that's the only one so far we have looked at which is not diagonal. But there were some things we tried for getting a given what you are asking, given a Lagrangian can I find, and we have often failed then succeeded. So I cheated and told you what worked, but.
Okay. So I also have a question. So in this case where you had alpha ij and beta ij, you set them to be constant. But of course, from this point of view of this Associahedron, alpha ij could be an arbitrary matrix n cross n, and then surely it would not work, right? If you took a non-constant matrix, or you could even take different matrices for different values of n, and then it would not work, right? Like I could take, this is a matrix which depends on, how, the number of external particles that you have, this map. So
I mean, it's a diffeomorphism between the two Cartesian spaces.
Yeah.
It's a linear diffeomorphism.
I know, but the Associahedra for 5 external points doesn't care about the Associahedra for 6 external points. In the combinatoric space, those are different things. So I
No,
could take
the Associahedra of 5 points is the boundary of the Associahedra of the 6 points.
I see. Okay, so let me ask the question. And if I take alpha ij to be some general matrix, do we still expect it will
No,
work?
we don't have an answer. You're saying not, like some degenerate matrix where something's
Not even degenerate, just a matrix.
No,
which,
yeah,
not a constant,
yeah,
not a C
yeah.
number.
I think structural analysis of what diffeomorphisms are allowed to give us physical S matrices, I don't know the answer.
I see. The second question is, you said everything goes through for one loop. Does that mean, so even
for the integrand.
But even when you have color ordered amplitudes, is this for just the planar part of the one loop amplitude? Because there now you can have non-planar terms also occurring.
So now actually the situation is much better, although the connection with Associahedra positive geometry is a bit implicit, that you take any, let's say phi cube, and take n point L loop integrand of this. No. You fix, so you can have multi-trace terms also, of course, but there's always a split into single trace, double trace, etc. Every such contribution can be obtained in terms of via some more complicated positive geometries, and that is realized in the Schwinger type parameterization, which I did not have time to go into. So you take a generic n-point amplitude, not planar or anything, you split it into color factors, and every term at arbitrary loop order in the Schwinger space can be obtained via these G vector constructions. So this is again work of Pinaki has to remind me, Nima, Carolina, Giulio, Hugh Thomas, Lamondan, and many others. But it's like series of papers which. So I think these are really.
And Hadley Frost probably. Yeah.
Thank you,
Good,
and
yeah.
Frost, yes. And these are really. I think this is a real leap in my opinion than what I have told you. I mean, yeah.
So I saw earlier two more people raised their hands since we're kind of running low on time. Let me just ask, because maybe I don't know, have some of the questions been answered, or someone have maybe a last question then.
In the original Associahedron, when we wrote this canonical form, there was this picture of projective scaling under which it's invariant.
Yes.
So now when you do this deformation, can you assign a projective scaling to different parameters like mass and alpha ij, under which this differential form is still invariant?
That's an excellent question.
Because that could give a constraint on which amplitudes you are
absolutely.
getting.
That's a very good point. I don't know. Yeah, I mean, it's true that the positive geometry form really crucially realizes projective invariance, as you said, and once you do these deformations, it's gone in some sense, and
maybe mass could be scaled in some way.
I feel that there is a lot more about these deformations we need to understand. That
Okay. Thanks to everyone for that good discussion, and so let's thank Alok. Let's thank Alok again. Sorry.